then if you had questions about like histopathology, you can ask at the end. I think that's a better way. All right, so I'm gonna search. Oh, I cannot share my screen. I think you have to give me.
Yeah, now you can. Sorry. Yeah.
Okay. All right, so let's go. Okay. Share. All right, that's not it. Okay. So I'm gonna start by the solution file because we're gonna go through it anyway, or perhaps start by the assignment and go back to the solution file. Okay. The first block of code we go through installing PyDicom, as we saw in the session on Friday. You have to install it because Colab includes some libraries by default, but not everything. So sometimes you have to install the library separately, which you can do like this because Colab is running on Linux, so you can use pip and treat it like a Linux command line. So that's installing PyDicom. That was the library that was discussed by Sebastian, and we're gonna import it here. We're gonna import NumPy, and NumPy is gonna be so useful. I think you already know about NumPy by previous sessions, and other like Matplotlib and other libraries that I'm gonna discuss in the rest of the notebook. So installing, importing, nothing important, but we need those. And we also gain access to some data other than the data that we discussed in the Friday session. So we thought like use another data set, so it's all new, and you also get to see other types of like 3D images. We found this brain MRI DICOM file on this link. It was free for downloading. It's a website called I Do Imaging, and it has some free samples for downloading, and it's available for public. And the way we also, it's useful to know like how to download data files into Colab. You can use wget. It's a command in Linux that downloads the link that you give it. So the data set that we downloaded is in zip file, and we downloaded it with wget. It will be downloaded, and maybe it's a good idea that I also run the code as I go forward. So let's run the first block. Also, I think you should have learned about Colab by now, but yeah, Colab has like many options. We're gonna use CPU today only because our work is mostly just demonstration. Nothing is going to be trained, but you can change the runtime type here. But okay, so we're gonna download the data, and then we're gonna unzip it. There's a command for unzipping as well because we download a zip file. You're gonna need to unzip it, and it will be downloaded beside your files. If you go to the panel on the left side, you can see the downloaded file. So it's the file we downloaded, and it's unzipped version here. You see that they end by .dcm, which means they are DICOM files, and they are the different slices of the image. There are 32 slices in this data that we downloaded. And okay, so we set the path for the folder that has our images. As you can see, there is a folder here called 1010 brain MR04Li, and we're gonna set a variable to have the path for that folder because we're gonna like use PyDicom to read the files from that folder. So this basically is that, just setting the path for that folder. Okay, so we're gonna go through the first exercise. I'm just gonna like show it from the clear file, and then we're gonna get back there and run it. Okay, the first exercise, what we decided to do was this question asks you to read all the DICOM files that we downloaded and extracted. slice by slice, and return the loaded slice in format of a single NumPy list. We're gonna discuss how to do that. And what we asked you guys to do and practice in this part of the code is define a function for reading DICOM files and sort them, which we're gonna discuss how it can be done. And also we ask you to access patient ID from DICOM objects using two methods, because if you recall, Sebastian discussed accessing tags and metadata information from DICOM files using many different methods. We're gonna just look at two of them for practice in this part of the code, and we're gonna do that. Okay, so we already had given you some sort of a template for the function that's gonna its arguments are dir paths that we defined, and we're gonna input that into the function. And we also have an argument called force, which I'm gonna discuss what it is, and it's gonna return the slices. The slices is going to be the DICOM files that we read, but in one object. Okay, so the way we're gonna do that is using PyDICOM DCMRead function. What DCMRead does is reading the .dcm files slice by a slice. So what happens here is we define a list, and this list is gonna involve all the slices. I'm not sure like if you have seen this type of syntax for defining a list in previous sessions or not, but one of the things you can do is, instead of using a for loop separately, you can just define the list like this and use a simpler syntax or like a shorter syntax like that. What it does is basically ask the list for PTH in sorted glob. What happens here is we mentioned that go and look at all the files that are in this directory, which was this. So go and look at all the files in this directory, which are 32 slices of the DCM files, and save each of the slices in a variable called path, and then input the path to pydicom.dcmread. And basically what happens here is each one of the files in the directory will be read by DCMRead and saved to a list. So this list will be basically includes all the DCM files, but read in PyDICOM. So our slices will include that. We use the sort function, and we use the instance number. Instance number basically addresses the, let me show you, addresses the number for like each slide, because like ordering of our slides matters in PyDICOM files, because for example, it starts from certain distance and it goes forward, which we will look at in the here. For example, let me see if it worked. I think I should run the code before being able to move that. But yeah, ordering of our files matter in the PyDICOM. So basically we sort them and we tell the Python to sort it based on instance number. We have something in chat. Let me look at it. I think you can also do that with the slice positioning. Maybe Kayhan, if you have any better idea, you can like jump in. But also instance number can work, and it will sort it out pretty okay. So basically, in programming, what happens is you have many different ways of doing one thing. So perhaps you could do it with slice positioning. I'm not sure about that, but instance number works fine here as well. Yeah, and also, like, if Kayhan, go ahead.
Yeah, I wanted to answer the question in the chat, but anyway, we usually need to sort the slices. We have the numbers glob.globs try to load all the DCM files based on the names. So, but those names must not be exactly the same as the original instance number. That's why we use the instance numbers inside the DICOM files to sort the slices based on them. And the reason is that those these type of images, they are 3D. So they can be something like time line images, or it depends on the type of the data, but in this case with the DCM files, we always use instance numbers to sort them. Yeah, and the time series data, in the time series data, we always need to sort them based on some criteria, but we are not sure about the exact names of the slices inside the folder. That's the reason that we prefer to sort them in one more step using the instance number. But about the positioning, it depends, I don't know, it depends on the task. If you need to sort them based on the positioning, it is another story. So, but usually the main goal of this sorting is just to sort the slices one after another to kind of reconstruct the whole slide. If we want to combine them at the end and create only one single 3D image, we trust on just the instance numbers, just that.
Okay, another question. Read DICOM files from multiple subdirectories inside a folder. I am not sure if you have that function in PyDICOM, but what you can do is like create another for loop. For example, you use the globe function to list all the directories, and then you use a for loop for each directory. You can use a double for loop. Kayhan, do you have a better answer?
Yeah, actually, you can do it using the glob.glob, but in this case, the format would be different. I will send you the format in the chat. So yeah, I will answer that question in the chat. You can just go on and describe the assignment.
Okay. All right. So I'm gonna run this block of code. Okay. So number of slices is 32. We check that by the length function. Length function works for strings, works for lists, and it's generally a useful thing in Python. And okay, so we had 32 slices in the directory, as I showed you. It's from 0 to 31, which means 32 slices. So we read all of them, and we're gonna check for the data type. Usually type function in Python tells you the data type. So we use only the first item of the list to see what data type it is, and it's PyDICOM dataset.file dataset, which is the correct format, which it should be. And if you check the original notebook from the Friday session, you see that Sebastian also have read the files in this format. Okay. So we're gonna check for the shape of the files that we have already read, and it's 256 by 256. So it means that we have 32 slices, and each slice is 256 by 256. So this is the interesting thing here. We created a function that using that you can, I'm gonna just zoom out a little. Using that, you can go through the slices of the image. So, okay, this is the first slide. As you can see, it's like almost outside of the brain. And as you go through, you can see that the images are slowly like going deeper and deeper. And you can see like it's all inside the skull, and like different sides of the brain is getting smaller again because we are going deeper, and we're gonna exit the brain, like I think on the last slice. Okay, so it was something fun we thought to put here. You guys can play around with it, but it's not part of the assignment, so it was already given. And it's a function called interact. It's for Jupyter Notebook specifically. You can play with its output on the output section of the notebook. But yeah, basically, this whole block was about looking at the data. It's always a good idea to look at your data before feeding it to a model. Always, I suggest always doing that. All right. So the second part of the first exercise was accessing the patient ID using indexing and the attribute. So using indexing, we can do something. We can like take a look at the, let me run this for you. So if you remember, we had all this metadata information on each file, and if you look at here, patient ID is accessed by 10, 20, so you can access it like that. And yeah, you can access the patient ID using the indexes like this, but you should also call the dot value attribute, which will give you the 10, 0. And you can also access the patient ID using dot patient ID and using the attribute. So there are two ways of accessing it, but they both bring the same results. I find this one like more convenient for myself because I don't want to go and look at the indexes. Okay, so that was the first exercise basically. And we just wanted you to read the files and save them in DICOM format, and also like access the patient ID. If you have like questions about this, you can either ask now, or you can also write it in the chat, or I can get back to them, and or maybe Kayhan can answer them in the chat. But yeah, that was the first exercise. All right. Second exercise. So this one was a bit of a more image processing type of exercise rather than working with PyDICOM. We thought like put an exercise that mostly focuses on image processing, and we can get you guys familiar with many different functions that are usually used for pre-processing image data. And okay, so if you remember, there was like an Hounsfield scale that was discussed in the Friday session, although very briefly. But we thought make a function to like do the transformation that was discussed in the session, and so you guys can see it in action rather than just hearing it in theory. So we had asked you to like define a function for that transformation and a window clip function. If I'm not wrong, somebody asked that can we keep all full range of the data, and what will happen if we, for example, keep all of it or throw some of it? I think it was a question that was asked on Friday, and we thought like include it, like we had actually included it already, and it was funny, someone actually asked it. And so this function is gonna like limit the range of the information, or like range of the pixels in the image. And the next function we asked you to design was converting the DICOM files into NumPy format and outputting a 3D NumPy object. And another one that was min-max scaler. It was also discussed in the Friday session. And if you remember, it was like a part that was mentioned when we looked at the pixel data. Sebastian mentioned that your data is not between 0 and 1, you can scale it. So we're gonna show you how it can be done, because it wasn't mentioned in the original notebook. So we included it here in the assignment. We can take a look at like how it can be done, how a scaling can be done. All right, so Kayhan, do you wanna explain these functions, because they were like mostly designed by Kayhan, or should I go ahead and?
Yeah, that's fine. If you want, I can just talk about them.
Yeah, go ahead. If you want,
okay.
you can better share your screen, or I don't know, how can I like give you
No,
control?
that's fine. You can keep it. Yeah, you can keep it shared. And also,
okay.
Yeah, for the to-view function, in this case, we just get the list of the loaded slices as we done it in the previous exercise. And then we go through it, and using the intercept and the slope extracted from the slices. And we know that it must be the same for all the slices for a single patient. So we don't need to set the variable all the time. So just we use the first slice and then extract those two variables and use them to just scale the original range of the slices to the new range. But if they don't have any rescale intercept and also rescale slope inside the patient data. So it means that we can keep them the same. Some people just set the intercept as minus 1024, 1024, or just 0. I think in this case, it would be better to keep it 0 and 1 for the slope if we don't have, or they have not been mentioned inside. So we just set these two variables at the beginning and then go through the slices one by one, and then just try to read the pixel arrays, which we know that is of type NumPy ND array, and then calculate the new scale. And the image would be image multiplied by slope plus intercept. And just create another list, empty list, and and add these scaled slices into that one. And yeah, that's it. So usually this function that we are talking about right now is for pre-processing, and usually when we want to use a model, I don't know if it is a machine learning or a deep learning model, usually deep learning because they are images, but you can extract a lot of features from this metadata. We didn't do that in this exercise, but I know that there are some tools that you can use to extract thousands of features from this data. But anyway, if you are going to use machine learning and deep learning models for training, you for sure you need to just scale them into the right scale that you want to work with. And the first step would be to just scale them to the hue or host field unit scale. As I know that usually they work with this type. And then after that, if you are interested in a special region, we are going to use a window clip to just zoom in that part and extract the features from the most important sections out of the image. So in this case, we define a window which would have a center and also width, and use it to extract all the kind of pixels that are in that range that is defined by the window. And as you can see here, we just make a copy of the image inside the for loop, and then all the pixels that are less than the minimum value, which is defined by the window, is going to be turned to the min value and also for the max value, because we know that, for example, in this type of images, sometimes we are not interested in the air inside, so we want to remove those area into a specific value. And yeah, this is the way that we do it using the window clip function. Yeah, and then the third one is just a simple function, because now we pre-processed all the slices separately and we just want to combine them, stack them into a single image. And in this case, we use NumPy functions, np.stack, and give it a list of slices. And then we would have a 3D image, which the first dimension of this defined image is the number of channels. I mean, the channel would be stacked as the first dimension. The second one and the third one would be the height and the width of each slide. And yeah, but in this function, you can define if you want to have, we have first channel image and last channel. If you want to have them to be last, the channels be the last dimension, you can just set it as axis is equal to -1. Yeah. And we have another function which we usually use for scaling these defined images into range 0 and 1. And based on this range, you can just transform all the pixels to any range that you want. But 0 and 1 is the base range for us. And usually with the deep learning and also machine learning methods, we usually use 0 to 1 range or -1 to 1. They are safer anyway. And also the training would be more stable and faster. So yeah, we designed this function. It is easy. So in this case, there is a formula for that, for scaling them min-max scalar as a min-max scalar. So just image minus image.mean divided by the standard deviation of the image, which is image.max minus image.mean. And if the user interested he or she can change the D type as well easily because it's a single image. So image.asType, we change the image type. And then there is a utility function at the end, which is a visualizer. So we use it to just visualize a single slice to see the differences between the original and also the transformed or scaled version of the same image. Yeah, that's it.
Okay, thanks, Kayhan. All right, so just go through this very quickly again. Someone asked in the chat whether PyDICOM doesn't already use a slope and intercept. It does, but when you want to transform your data to the Hausen field unit scale, you have to do the multiplication and summation again using the already.
Yeah. If you mean PyDICOM.dcmbreed or those functions that we use to load the images, they must not do it, but some functions, they have it by default. True, but I think that DICOM doesn't apply that one because it's kind of more stable. If the user wants, he or she can use the intercept and slope as they are present as an attribute inside the DICOM file and then scale it. But by default, no, there is no, I mean, it's not going to apply it directly.
No. So yeah, if you want to transform it to another type of data like house field unit, you have to do the multiplication and summation. All right, and just one thing. So if you remember from the Friday, that pixel array will return to you NumPy format. So that's why we can do the multiplication and summation very easily on the data, because when you call that pixel array, it returns a NumPy, and NumPy is basically a matrix of numbers that's like handled in Python very easily. Okay, so we saw the functions, and now we're gonna see their use and how they make difference to our data. And zoom out a little. Okay, so basically at the first line we call the .toHue function and we feed it the slices. If you remember, the slices was a list of DICOM files in the PyDICOM format. So we're gonna input that to .hue function. It's gonna output, we're gonna save its output to an object called process the slices hue. We're gonna input that one to the window clip. So window clip will, here we defined, we gave the window clip function two arguments, 500 and 1000. 500 will be the center that we're interested, and the 1000 will be the range that we are interested. So basically, minimum value that we are interested is 500 minus 1000 divided by 2. So it's 500 minus 500, it's 0. And here 500 plus 500, so it's 1000. So basically, we keep the values from 0 to 1000. And yeah, if you look at the output, basically the transformed image pixel range will be in 0 and 1000. And the output of the, okay, the output of the 3D NumPy, we also had a function called 3D NumPy. Basically what it did was it used the PyDICOM, it used the slices that we read with PyDICOM, and it stacked them using NumPy and returns the NumPy format to you, even though that pixel array returns a NumPy format to you, but we want to put all the slices into one NumPy file. We don't want multiple, we want one NumPy object. So we used np.stack to stack all the slices together, so we have one object. So 3D NumPy basically returns to you that object that I described, then we call it image. So the format of the image will be 32 by 20 256 by 216. And also, like, because we did the transformation, so it basically changed from 256 to one of the sides from 256 to 216. And transformed image pixel value, we printed the range that we kept. It's from 0 to 1000. And eventually we did the scaling, and the min-max scalar function that we defined gets the image as input, and we'll bring the we'll bring the 0 to 1000 to 0 to 1. So basically before scaling, our values that we kept was between 0 to 1000, but we used the min max scaler function to bring the values, the pixel values from between 0 to 1000 to 0 to 1. And Kayhan described it. The reason we do this is because we want to have a easier time training our models. Machine learning models work way better when your data is normalized. And also, I just need to mention that as Kayhan mentioned, there was a formula for doing that. We minus the data from its minimum value and divided by the range of the data. The range of the data is defined by maximum value in that data minus the minimum value. So this is range and this is the minimum. And if you subtract the minimum from all the values in the image and divide the values by the range, what you will get is a format that will end up being 0 to 1. So we also visualize the result when you do the Hounsfield transformation. This is how your first slide will look like. But then after doing the window clip, keeping the values between 0 to 1000 and then scaling them between 0 to 1, what happens is your data will be transformed to this version. As you can see, it's easier to notice different things in the second image. So it's not only it makes it easier for our models to work with, but also it's easier for a clinician to look at the image. And because this one, if you notice, it's a bit darker, but this one is brighter, and also details like these lines here are more easily visible. So that was the second exercise, and what we did mostly was pre-processing the image and transforming it into a new format and scaling it. All right. There's something in the chat. Maybe will comment images, MRI image. This is not the.
I will answer the question in the chat. That's
sure,
fine.
Sure. All right. And exercise 3, saving the data in NumPy format. It's exercise 3 is basically just saving the data into a NumPy file. It's nothing specific. You just wanna, after you do all the transformations and all the scaling and everything, you want to save your file, because usually when you are working with data in Python and generally for machine learning and deep learning, after you do a lot of pre-processing, you want to save your data, because every time you run your code, you don't want to go through all that pre-processing. You want to have it saved, so next time you want to use the data or next time you want to run your code, what you can do is just load that already pre-processed data, so you don't have to spend time, because here our data set is small and it doesn't, it's not a really big deal, but sometimes you have a data set of 1,000 million images, and they are really high resolution, and it takes maybe a day to pre-process them, and if you want to do the pre-processing every time, it's gonna put your work really behind. So you're gonna have to save what you have already done. So that's the exercise we're gonna discuss. In this exercise, we save the files in NumPy format, and also we save them in one object, and also we save it a slice by a slice, just for the sake of practicing. But usually what I do is just save them as one object. So what happens in this one is we use the function that we defined to 3D NumPy, and what we do is we just save the original NumPy version. Original NumPy version was the image before all the transformations, so slices was our initial list, and we want to save the initial data in case we needed it sometime, and we don't want it to be lost in all the transformations. So we save the data as the original NumPy version. NumPy has a function called .save. If you input an NumPy object to this function, it will save it, and you can define the extension that will be saved in, which is .npy. So you can save this. Let me run the code. I have to run the other blocks. Okay, we define the functions, we do the transformations, and we save it. Okay, so the original data is saved in original NumPy version, and we save the scaled slices, slice by slice, in a new folder called scaled slices. So now if you check the contents of the Google Colab, what you can notice is we have a file called original NumPy version, which is your initial data, but only saved in NumPy format and in one object, not in multiple slices. And we created a, sorry. And we created a new folder called scaled slices, and we saved the slices in NumPy format one by one, but we could also save the scaled version like what we did up here. So we could like save it in one object like this one, but we just did it separately because we wanted you guys to like see it can be done, and it was just for the sake of practicing. But if I do this, and I only need to like call the scaled image and called it like scaled image, and like if I call this function, what happens is this will be saved as well. So you have it a slice by a slice in NumPy format here. You also have it as a 3D image here in one object.
Yeah, the main goal of this exercise was to just prepare the images for later usage. For example, you scale them, you prepare them, you do the pre-processing, and just store them as a folder inside a folder or as a single file. If you want to have them prepared for the I don't know, we have 3D models like 3D unit for segmentation, or I don't know if you want to work, just load and work them for classification or whatever. You may need it to be a single 3D image. That is one approach, that you can save them separately as for each patient as a single file. Or sometimes you want them to work as a, I don't know, as a 2D models, as a 2D images for 2D models. So in this case, you can save them inside a folder, but the point is that they are ready and you don't need to do the huge pre-processing while you are training your model, which takes a lot of time. So
Yeah, exactly.
You have them saved, prepared, and at the end, you just need to define your model and train it on these prepared images.
Yeah. Okay, and the final exercise is the converting the NumPy data, all the transformations and everything that we did, the scaling, back to DICOM format. And yeah, and again, we're just doing this for the sake of practice. We usually like, because machine learning models, they all work fine by NumPy, and they don't actually get DICOM as an direct input. They all get NumPy format as an input. So, but we save them as DICOM again, because sometimes we just want to do the transformations, save them for whatever reason to DICOM again, because DICOM includes a lot of meta information, metadata that like NumPy doesn't. NumPy only includes the pixel array, but if you want to do the transformations and then save it back to DICOM, so you also keep the records about the perhaps patient information or like the different things that you can get from the DICOM. You can save the NumPy back to DICOM, although it's not as easy as saving DICOM to NumPy. DICOM to NumPy is pretty easy. It's like 1 or 2 lines of code, but actually saving the NumPy to DICOM is a little bit more complicated. So the function that we define goes through. We first define a new directory for saving the DICOM format that we require. As we can see, it's not already here, so we have to make it. And also, I can quickly mention this OS library is a library in Python. It does a lot of things for you. One of the many things that it can do for you is just creating a new directory and make dir or make dirs. What it does is create a directory for you with this name. So we ask it to create a directory because we want to save the DICOM slices. And what we do is this line of code is a little bit complicated for beginners to Python, but nothing is specifically complicated is happening. Just we are going through the previous and initial DICOM file that we had, because it includes all the metadata that we still require and we want to save. But we also go through the new new slices that we created. And I think this one is, oh yeah, it's after the first transformation. Yeah, so we are saving the file after the first transformation. We can also save it after like the other ones, other transformations, but like it's already in NumPy and we're just trying to save it in NumPy. So what we do is we go through the slices that we had, initial slices, the first PyDICOM file that we read, because it includes all the metadata. And we also go through a NumPy version of our data. And what we do is there are elements in the slices. If you recall from Friday, each DICOM file included many different elements. And what we want to do is get those elements from the initial DICOM file that we read and write them to the new DICOM file that we want to create. So what we do, what happens in this line is we mentioned that for element in SLI, SLI is already inside the slices. I mentioned this line of code might look a little confusing too, but it's nothing confusing. Instead of like writing multiple for loops, what we did is just use enumerate and zip, and what it allows you to like read I for the indexing, and SLI image comes from this NumPy array here, and SLI comes from here, and it allows you to simultaneously iterate through all of this. So basically, so what it does is we go through elements in SLI. SLI was already inside the slices, so slices is our first PyDICOM file, and we read the elements and we check if it's about the pixel data. So if it's about the image and the numbers in the image, what we do is we convert it to bytes, and we create data element and we add it to the data set. And also we have to create a new data set before creating a new DICOM file, and we will save that data set. So remember that you have to create a data set object. Data set object is can be imported from PyDICOM library. So what we do is like we read the pixel data, we convert it to bytes, and we add it to the data set object. And if it's not pixel data, it's like other information, we just directly add it because it doesn't need to be converted into bytes or anything. And at the end, we also like made sure that the rows and columns are the same as like what we are writing into the image. And if you remember, it was 256 by 256, but I think the transformation got it 256 to 216, if I'm not wrong. So we are enforcing that, making sure that these values are set correctly, even though I think rows and columns are already included in the elements. So, well, we're just putting it here for making sure. And there are some required variables that has to be set, and we create a metadata set object. And although like they were already included, you can, I think you can like, well, I think you need it, but I'm not sure. But yeah, anyway, so most of the information is transferred from the previous DICOM file into the new one in these lines, but like we just included these to make sure and demonstrate to you that what's happening. And we finally like save the data as .dcm. And if I run this lock right now, what happens is the new directory is created, the scale slices, and all the DCM files are written here. And all right, so what we do here is we read them back, making sure we have written the correct slices, and we call them slices new. Load the slices from scale slices DICOM, which was the directory that we created here. So we read it back again using DICOM, and the number of slices is 32. The format is correct, and eventually we just gonna, oh, sorry, okay, accidentally entered twice. Okay, and what we're gonna do is just read them back. So as you can see, when we read them back, you see that the transformation is applied. And for example, if you look at the slice 15 here and slice 15 up there, you see that this was very dark, but we did the transformation and we saved it to a new DICOM file. And when you read it back, the transform file is present here. So you did all the pre-processing and transformations, you saved it, you read it back, and you can use it later. Like, for example, you did all the pre-processing, you save it, and you can use it later for your model, or use it later for clinician examination, or anything else that might come to the mind. I think that was it. I'm done with the exercise. If Kayhan wants to add anything, or if you have questions that I can answer.
Yeah, I think everything is clear. If you have any question, you can ask.
Okay, if anything you haven't answered in the chat.
Yeah, I actually answered anything in the chat, so.
Okay, thank you. But like, if you have anything that you want to ask, you can also connect your microphone and like ask me directly. Yeah.
You know,
Yeah,
it
but
seems
most.
like
Okay,
yeah,
okay.
it seems like
Sorry,
there's a question. Sorry, go ahead. Yeah, sorry.
Yeah, I just wanted to add something. Like, mostly it's just gonna be if you want to enter like machine learning and deep learning, it's mostly gonna be working with NumPy array. So PyDICOM, I think mostly will be just used to read the data and perhaps going through patient information or information about the recorded images, but you won't directly use it with machine learning models. Like, based on my experience, like, it's always NumPy, because it's very, very optimized to work with CPU and Python. So PyDICOM and DICOM files are a bit heavy and like not really optimized for machine learning. So that's why you will usually convert them to NumPy and then use the NumPy. Yep, all right.
Yeah, that's it. Thank you guys so much, Moeen and Kayhan. Yeah, the quiz for this the workshop is available, and I've recorded this, so like we'll look into putting up the recordings on the same playlist as well. With that, if there's no more questions, I see everyone is thanking, so that's it. Thank you so much. See you guys in later workshops. Yeah. Bye.
Thank you. Bye.
Goodbye, everyone. Have a good day. Okay. Actually, there is a question. Are you going to answer that? Or?
Okay. Oh, the recorded video. So they'll be on the same YouTube playlist as the rest of the workshop. So the emails that you get, they have like a unlisted playlist. I think I'll put it in the Discord so that you guys see it. Let me see if I have. Since we have time, I'll just do it right now. Nice. Yeah, so all of the videos and the contents should go to this playlist. It might take us like a while to retrieve them and convert them and upload them to YouTube, but like they'll be there anyways. Yeah. So I think with that, we can end the session and have a great rest of the weekend, guys. Bye.